Hello and welcome to the final presentation for Team 2 for Class ME452. Our team has decided to do an analysis and redesign of a table lamp, and our team members include Shivastu Kartik, Noah Nisley, Nathan Lang, Noah Mikey, and David Wells.
The product chosen to be analyzed by our team is an adjustable table lamp. An adjustable table lamp is a light source with modular light intensity that can be mounted to a flat surface, ideally a tabletop, and positioned with certain degrees of freedom to meet user lighting needs. The adjustable table lamp analyzed by our team utilizes springs and extra joints at its head and base to assist in maintaining lighting position. The primary customer group for this product are general purpose users that simply need a light source, such as homeowners and students alike. The secondary customer group for this product are working professionals and hobbyists, such as architects, workshop owners, and comic book artists.
To conduct a functional analysis of our product, we developed a fast diagram. We began with the task function of the product, which is to project light. To do this, we would have to support the light source and move the light source. To support the light source, we would have to maintain its position and distribute its weight. And to move the light source, we would need to enable movement in the X, Y, and Z axes. We also addressed some supporting functions that would enhance the product. To do this, we would maximize the degrees of freedom, we would enable comfortable positioning, and we would add resistance. We used the fast diagram to develop our functional component mapping matrix, which correlates the components in our bill of materials to the functives developed in the fast diagram. The most commonly addressed function is to maintain position, with 7 out of our 13 components being involved in supporting this function. Conversely, the head joint is the component that addresses the maximum number of functions.
The first step in our product family design is to create a functional differentiation table. This table takes the levers of our fast or our functives and separates them into two groups, those that are the same between the customer groups and functives that are different. Comparing this with the functional component mapping matrix yields us with the component commonality table, a table showing which parts will be common and which parts will be unique to the variety. Module 1, or the knob, was redesigned to have a larger shape, as well as more points. This should facilitate more comfort for users adjusting the lamp. The second module, the base Fulcrum, was also redesigned. As you can see on the left, the original design contains a tab that limits rotation in the vertical axis. However, the redesign features a slot that allows for 180 degrees of rotation about this axis. It should be noted that this part is very similar to the original design and will likely be able to be manufactured using the same die sequence. Lastly, we have an assembly sequence with delayed differentiation. The top shows the assembly sequence that we saw earlier, and the bottom shows its redesign.
To design for manual assembly, we first performed an assembly sequence analysis. As you can see here, many steps have low assembly efficiency scores and lots of opportunity exists to redesign. The two parts we've chosen to redesign, the elbow plate and the fulcrum, both have low assembly efficiency, as well as serve multiple functions shown by the functional component mapping matrix, and have been identified in the quad chart as parts needing redesign or elimination. First redesigned part, the elbow plate, was changed to incorporate 2 of the fasteners into the plate. This change not only reduces the part count and the need for fasteners, but it also serves as locating features for operators. Likely, this part will be more expensive to produce than its original due to its necessity to be manufactured in a different manner. However, it will reduce the cost of fasteners that must be included. The second redesigned part, the fulcrum, was redesigned to have 180 degree symmetry about the beta axis. Additionally, screw threads have been added to eliminate the need for nuts. This version will be more expensive to produce as it relies on secondary machining processes of tapping and turning. However, it reduces the part count by eliminating the nuts. Finally, we performed an assembly sequence analysis again with the redesigned parts. As you can see highlighted in red, the efficiency of both redesigned parts, as well as some of their mating components, has improved, and the total assembly time has decreased by about 22.5 seconds.
The platform subassembly chosen to be analyzed for design for automated assembly is the base Struct subassembly. The base Struct subassembly contains 2 base tensioner springs, 2 elbow plates, the base back Struct, base front Struct, and an elbow anchor. Within this subassembly, the base tensioner springs, elbow plates, and elbow anchor will be analyzed for automated assembly improvements. To justify these part choices, we can refer to the quad chart. To further support these choices, we can focus our attention to the functional component mapping matrix. For these reasons, design revisions for automated assembly were conducted on this subassembly, and the results are outlined in this table. So to improve the base tensioner springs, we included a plastic casing that would go around or enclose the tensioner springs. This change would improve or decrease the amount of tangling that would occur, ultimately increasing the handling and increasing the max feed rate, which would then result in a decrease in handling feeding cost. For the elbow plates, we decided to improve the symmetry in all axes of this part to make it easier for feeding, and also we decided to include flanges or extrusions at the edges to decrease overlapping, which all culminated in a decreased handling cost by improving feed rate and also reducing relative handling cost.
We now address process selection for the components that were modified during DfM. The first of these is the fulcrum, and the critical dimension is the diameter of the shaft element. This is because according to the functional component mapping matrix, the fulcrum fulfills the maintain position function, and it does so by having the shaft mate with the bearing on the base plate to secure its position. The tolerance for the diameter of the shaft element was therefore selected in accordance with the requirements for a clearance fit. This table shows the process selection for the fulcrum. Machining and die casting were found to be suitable processes, and our final recommendation would be die casting for the base shape, followed by machining of the shaft element to achieve the critical tolerance that is required only on the shaft element. The next component we address is the elbow plate, and the critical dimension in this case is the distance between the holes. This is because according to the functional component mapping matrix, the elbow plate fulfills the maintain position function, and the distance between the holes enables the elbow plate to mate with and secure the position of the other adjustable components in the assembly. The tolerance for this dimension is 10,000ths of an inch, which is looser than the bearing because the elbow plate only mates with the adjustable components, and since no tight fits are required, looser tolerances are acceptable. This table shows the process selection. Machining, sheet metal working, and die casting were found to be suitable, and our final recommendation would be die casting for the base shape.
Here on the right, the elbow plate previously mentioned and redesigned for assembly is displayed. An analysis was performed in order to determine the cost of manufacturing this component. This component will be die cast out of aluminum, and we found that the total cost to manufacture came to $0.7125 per part. It was decided that this was a high manufacturing cost, and it could be reduced with simple modifications. The new design can be seen here. The first modification was to reduce the number of pulls performed during the die cast, which was guideline DFDC6. This means that we won't have the threads from the die cast and will have to be machined on later. But this was deemed a worthy trade-off. Next, fillets were added to the screws in order to reduce sharp edges, which was guideline DFDC4. Finally, a drafting angle of 5 degrees was added, which was guideline DFDC3. After performing these modifications, it was found that the difference in material cost is negligible. However, the operating cost and die cast costs are significantly decreased. The new total cost was found to be $0.5937 per part, giving a total reduction cost of $0.1188 per part. If the estimated production amount of 100,000 lamps was reached, this would save nearly $24,000.
Here is the DfM for the Fulcrum after design for manual assembly. It is machined out of solid aluminum block, bandsawed to rough shape, then milled, turned, and drilled, leading a cost breakdown as shown here with a total cost of $978 per part. For DfM, first we die cast it to a near net shape as seen on the left, DfM C1. Then we standardized the turning step to a standard size, DfM C3. Then we added a fillet at the bottom to DfM C11. On the right you can see DfM Pro suggesting that same fillet. After applying the DfM, we have the cost breakdown as seen on the left with a total cost of $249 per part. No impact on function/assembly cost due to same net shape. Here is the 3D Hubs cost estimation, and here it is compared to the analytical method. 3D Hubs shows a similar trend, but is significantly less due to the very large extrapolation between the number of 3D Hubs quantity and the total order quantity. For design for product service system, decided on a leasing of the lamp system. Customers are happier due to firm replacing and upgrading old lamps. Prices can be lowered due to firm able to release older lamps that the first customer was not using, and allows for firm to reduce waste by repairing and recycling old lamps. Design for manual assembly went down by 23 seconds per part. Design for automated assembly went down by 60 cents per part. If we started over, we would add electronics/light bulb, alternatively 3D printing the pieces beforehand to give an idea of assembly time. Thank you all. Is there any questions?